Suppose an event occurs with an average frequency of lambda. The probability that the event will occur alpha times in interval t can be modeled using a Poisson distribution. If the frequency is lambda, then the expected number of occurrences in this interval t will be lambda t. And so that gives us a Poisson distribution. Now, if we want to consider the waiting time, the waiting time before the event occurs alpha times will be at most t is the same as the event occurs at least alpha times in time t. But this is complementary to the event occurred less than alpha times in time t. And this event will be the sum of the Poisson probabilities, and we can express that in sigma notation as so the probability that the waiting time before the event occurs alpha times will be at most t. That'll be complementary to that sum. Now, since t is a continuous random variable, this is actually a CDF, and so we can find the PDF by differentiating the sum. And so we get and let's go ahead and simplify this. We'll remove our common factor. We'll reindex the series. But notice that except for the index variable, the two series have the same terms, but they have opposite signs, so almost all of them will cancel. The only other difference between the two series is that our second series includes one more term which doesn't get canceled. And so this summation is, and we can simplify that too. Consequently, suppose an event occurs with frequency lambda, the probability that alpha occurrences of the event occurs on or before t equals t has PDF, which is just the gamma distribution where alpha is a whole number. For historical reasons, this is also known as the airline distribution. For example, suppose a major flood occurs on average every 5 years. Find the probability a second flood will occur within the next 10 years. Note that we could find this without the gamma distribution, since this is complementary to the probability there are 0 or 1 floods in 10 years. We'll use the gamma distribution, but verify our solution using the Poisson distribution. Our PDF has lambda equal to 1/5 and alpha equal to 2. And so for that 10-year period, we'll integrate that over the interval from 0 to 10. Using integration by parts, we obtain Meanwhile, over a 10-year period, we'd expect 10/5 2 floods, so the probability of 2 floods in 10 years is complementary to there being 0 or 1 flood. And so we find which is the same as the probability we found using the gamma distribution. Now, note that when modeling the time before a number of Poisson distributed events occurs, using the gamma distribution requires the same work as using the Poisson distribution. This corresponds to the cases where alpha is a whole number, and so that raises the question, why would we use the gamma distribution? Turns out there are some good reasons to use the gamma distribution. For example, it will be on the test isn't one of them. But it will be on the test, so let's take a look at a few examples before returning to the rationale for the gamma distribution.